Okay, well, let's talk about radical chemistry. Everything we've done so far has been two-electron chemistry. Lone pairs on a heteroatom or two electrons in a pi bond acting as nucleophiles. However, there's a whole other class of intermediates, reactive intermediates, that we haven't talked about so far, and they are radicals. These are things with unpaired electrons. At least one unpaired electron. So carbon-based radicals, you can, let's see, carbon-based radicals you can think of in terms of stability just like carbocations. So a tertiary radical is more stable than a secondary radical, which is more stable than a primary radical. And presumably these are, which is more stable than methyl radical. So presumably you can think of carbon radicals as electron deficient species, and they are stabilized by the same things that carbocations are stabilized, presumably because of hyperconjugation. Now, their structure is interesting. Generally, it's fine to think of radicals as being, and I'll just draw a methyl radical, as being sp2 hybridized, planar, with the single electron unpaired held in a p orbital. Not empty, not filled, just partially filled. Okay, so there's some evidence that radicals can sort of pass through or sort of equilibrate with a more pyramidalized version that would be closer to sp3 hybridized. And that's an issue that's not really important for our discussion. For everything we're going to do, you can think of radicals as though they are sp3 hybridized. But it's possible for the radicals to sort of, basically the hydrogens around the periphery here can flap upwards and downwards, and it's pretty easy for radicals to do. All right, there is some question sort of off to the side about whether you need to know the mechanism for creating an epoxide. Yes, we did use MCPBA for creating an epoxide. And yes, I did show you the mechanism of it. Yeah, I'm not sure where in the text it is, but I definitely showed you in the lecture notes. Okay, so the same things that stabilize carbocations can stabilize radicals. That is, resonance stabilization works as well. If you think about a simple allyl radical, that is where the unpaired electron is on the at an allyl position, you could draw a resonance structure in which that unpaired electron would also be on carbon 1 instead of just on carbon 3. And if we look at the MOs, the pi molecular orbitals for the allyl system, what we conclude is the same thing we concluded for allyl cation and allyl anion. That is, the electron on carbons 1 and 3, the unpaired electron there, is only on 1 and 3 and never on 2. So resonance stabilizes radicals. And that'll be important in a little bit. So how do you generate radicals? Well, any questions so far about what a radical is? The dot represents an unpaired electron. Remember that unpaired electrons have spin. Well, all electrons have spin, and radicals are species with non-zero spin because they have an unpaired electron. That won't, the spin property of electrons won't really be important for us in this class. Now let's talk about how you would generate a radical to begin with. Basically,
hey professor.
Whoa, there we are. Okay, go ahead.
Sorry. I was just going to ask, this is kind of a dumb question, but is a radical, are we just talking about the lone electron, or are we talking about the molecule with the lone electron?
Okay, good question. The question is, and sorry for being surprised. I didn't mean to say, whoa, as though it were a bad thing to ask. No, you are always welcome to ask questions. In any case, the term radical, does it refer to the whole molecule or just the unpaired electron? A molecule with an unpaired electron is a radical. I think you could probably use the term radical to describe both things. So does that help, Emma?
Yeah, that makes sense.
Okay, yep, no problem. All right. So where do we get radicals from? Generally, you're looking for weak sigma bonds, and then you need to apply enough energy to take both of the electrons in the sigma bonding orbital and give one to either partner involved in the bond. So one of the ways your text uses to make radicals is to start with bromine. We already know the bromine-bromine bond is fairly weak. We've used it as an electrophile previously. But then we're going to excite the electrons in this bromine-bromine sigma bond with UV light. Now, organic chemists don't like to write long lists of things, write long words when a abbreviation will suffice. So often we abbreviate UV light with the following H Greek letter nu. That's the energy that would be contained in a photon of frequency nu, and H is Planck's constant. So this represents a photon of UV light. And so we'll follow that convention. I don't care that you show that you can replace the Greek letter with just the letter V, and that's fine with me. What this does is it breaks the sigma bond between the two bromines, and you get two bromine radicals. All right? And we have a particular way of pushing arrows for radical reactions. When we've been doing two-electron chemistry, we've drawn an arrow that had two little flags at the end. But with radical chemistry, to represent the movement of just one electron, we'll use a half-flagged or fishhook type arrow with only one flag. And that communicates movement of one electron. Okay, so notice that the bromine radical is neutral. It has 7 electrons. The other way of getting radicals, in addition to using UV light, is to start out with a weak sigma bond and then to add heat. So I'm putting an R group here. R means hydrocarbon or hydrogen. If you add heat, you can excite the bond. Adding heat causes, if you envision the bond between these two oxygens to be like a spring, adding heat starts to increase the vibration of that bond, and eventually you get to the point where they're far enough away that the bond doesn't exist anymore. So you can make that bond break with heat. Chemists, again, typically don't like to use the word heat. Instead, they will use the Greek symbol delta to indicate heat. And we'll follow that convention as well. Heat can take the peroxide and break the oxygen-oxygen sigma bond and cause one electron from that bond to go with either oxygen. All right. Steps where we generate a new radical in terms of mechanism are called radical Initiation. Now that sounds like something that Homeland Security is working on to detect domestic terrorism, but actually we just mean creating a molecule with an unpaired electron. All right, question so far? Yeah.
You can give me a quick answer to this, because it's getting like probably too in depth, but when you have that like splitting energy, the Planck's constant times, is that for one electron then? And that's why we generate where just one electron moves up in stability?
Okay, so the question, this is a good question, Hannah. Does this energy represent the energy for one electron or for two? The physical chemists could tell you better. I don't know. I think, in my mind, it represents the energy required to get from HOMO to LUMO, and if you jump from HOMO to LUMO, you break a bond. But I see what you're saying. Do you have to promote each electron individually? I think you promote one electron, and then the molecule falls apart.
So why is it then that we do end up with a free electron?
So why is it that we end up with an electron on either bromine?
And they don't.
I suppose that's the most stable way for it to fall apart. The other option would be this. And Br plus is unstable. I don't think I've answered your question, and I think a detailed answer to that question would require more knowledge of physical chemistry than I have, unfortunately.
That's good though. It makes the stability answer make sense, because it would make sense to have a positive charge.
You know, we envisioned, say, a bond in hydrogen, a sigma bond. Here's the sigma bonding orbital, and here's the sigma star, and here are your two starting orbitals. If you promote an electron up there and the bond falls apart, then the two atoms can go infinitely far apart. And as to why each one gets an electron, yeah, I don't know that I can provide a good answer to that. Okay. Oops, I want to figure out what I can erase and what I can't. Got rid of the Br. All right, so let's talk about some chemistry that these radicals can do. If you take a hydrocarbon, and this is our first reaction where this is the case, if you take a hydrocarbon and you expose it to bromine in the presence of light, you can actually replace one of those carbon-hydrogen bonds with a carbon-bromine sigma bond, and then a hydrogen-bromine sigma bond. So this is our first example of CH functionalization. That's a term you don't need to remember, but it's a special reaction because you can take a hydrocarbon where there's no good leaving groups and do a reaction that puts a good leaving group there. Now you've got a more useful molecule. Now, this reaction isn't the solution to all of our problems for generating useful chemicals from things that you can find in petroleum, but it is the first one that we're learning where you can do this. How does the mechanism work? Well, first you've got to do an initiation step where you generate the bromine radical. But then the mechanism consists of the following two steps, and we call them propagation steps because each of them starts with a radical and ends with a different radical. So here is the hydrocarbon, and here is the bromine radical. What will happen is that the bromine radical will attack one of the hydrogens to create a new bromine hydrogen bond. In so doing, it will take the hydrogen and one of its electrons. Now, if you want, you can think of this as HOMO attacking LUMO, though it's a little tricky because it's single electron chemistry. So, you can think of a single orbital dumping itself into the carbon-hydrogen sigma star, and then what happens next is just all about getting to the more stable products. But I'm not going to ask you about how the orbitals work with these radical reactions. This step is often called hydrogen abstraction. It's not proton abstraction. You're actually removing hydrogen and its electron from the molecule. That changes your hydrocarbon so that you have an unpaired electron left behind on the carbon, and then you have the new sigma bond that you made between hydrogen and bromine. Some people in drawing radical mechanisms will draw another arrow here representing that the other electron is left behind on the carbon. That's fine. It's also implied just in what we've drawn there. We took hydrogen and one of its electrons to make a new hydrogen-bromine bond, and we left the other electron behind on the carbon. All right. Wallace, I'm noticing a lot going on in the chat, but I think I'm missing stuff. Is there anything that I need to answer?
I don't think so. I think the only question that you're not going to answer is just why are these radicals stable enough
Okay.
to exist?
Yeah, why are the radicals stable enough to exist? In part because they're neutral. But you are right, they are reactive intermediates. They are short-lived, and many are very difficult to observe. Now, there are radicals that actually you can store indefinitely at room temperature, but this kind of radical is fairly unstable. And in fact, most of the time, those two bromine radicals will just recombine to form bromine, while they're still close to each other. In any case, actually, I want to go back to that. The reactive intermediate is short-lived. It will either recombine to form the bromine starting material, or it will do a propagation step. And generally, radicals are so reactive, and we've put bromine in a solution of cyclohexane. There's a lot of cyclohexane there. Probably the most common thing to have happen is this first hydrogen abstraction step. All right, anybody want to ask anything about this mechanistic step? It's unusual, you haven't seen something like this before. Go ahead.
Would something other than a radical be able to react with that one electron, or will it always be, because it has to happen so close to that molecule that it would always be able to do?
Okay, I'm not sure I understood the question. Will the radical be able to react with?
Anything like, so on the second step, where there's just like a hydrogen and an electron,
Okay.
would it interact with anything else, or just like that?
Okay, so the question is this going to react with other things, or does it stay as it is? No, this is also very reactive. So what it will do, at any given point, most of our bromine exists as Br2. So it will actually do a similar step where the single electron on the carbon removes bromine with one of its electrons to create a new a new carbon bromine bond, and you make a new bromine radical. This is why we call it a propagation step. You start with a radical, you get a radical out. And so this is kind of a new kind of chemistry because it has no beginning or end, right? Once you have some of the radical, there's a chain that continues to go on forever. I'm sure there's a gospel analogy in there. Maybe we need to edit if you could hide a collab to talk about how there is no end to radical propagation steps. Except there is. After a while, if the concentration of radicals starts to build up, you can have these rare termination events. And this is where one bromine radical finds another bromine radical. They recombine to give you not a radical, or say a carbon radical finds a single bromine radical and they recombine to give you a product that we made earlier. And you will even find under certain conditions some of the carbon radicals finding each other to make things that you didn't necessarily intend to make. But all of these, especially the ones where the carbon radicals have to be found, are present in vanishingly small amounts. Because most of the time when you do this reaction, every bromine radical is surrounded mostly by cyclohexane molecules that are not radicals, and so it's easiest to engage in these propagation steps. So we've sort of got a lather, rinse, and repeat cycle going on again and again, and sometimes you'll hear about it's a chain reaction, usually when the warp core of the Enterprise is about to explode. But see, nobody knows, nobody gets any, fewer people get Star Trek references than get references, say, to Star Wars or The Office. But I grew up when Star Trek The Next Generation was just out, and that was pretty cool. Until I realized that most of the science they were talking about was made up. It's disappointing. All right. Yes?
So why is it more common for it to break a new bromine bond than to just take one than to do the termination step?
Yeah. Why is it more common for the carbon radical to break a bromine-bromine bond than to just do the termination step? It has to do with the fact that radicals are high-energy intermediates, and therefore their concentration is low. And so the odds that one radical finds another are pretty small. Okay, other questions? If you could make a radical in the twinkling of an eye, and then propagate them onward with that same speed to fly. This is good. Keep going. Do you think that you could? Okay. Now, there's a lot more we could say. Bromine is pretty selective as a radical, as far as radicals go. So if we make our molecule just a little bit more complicated and put a methyl group on it, suddenly we've got all kinds of hydrogens that could react. I'm just drawing the different kinds of hydrogens that are present here. But it turns out that the only thing we observe when we use bromine as a product in this radical reaction is the one where bromine ends up on the more substituted carbon. And that is because the radical on the more substituted carbon is more stable than radicals on any of the other carbons in the molecule. So radical bromination is regioselective for the product where bromine is on the more substituted carbon. Right? We don't observe this or this or that, and I'm sorry, the penmanship is decreasing in quality. Do you see that? There were many other options for hydrogens that we could remove and abstract and then do radical chemistry, but the only position that gets modified is the more substituted one. Okay? Questions? All right. trying to think about what we want to do here. You can do this type of chemistry not only on hydrocarbons that are saturated, but you can also do this on molecules that have double bonds. If I use radical bromination conditions, I will selectively install Br at the allyl position. And that is because when I do my first propagation step, it is better to make the allyl radical, because the allyl radical is resonance stabilized. Now it just so happens that that allyl radical is symmetrical. Carbon 1 is the same as carbon 3. So either way, you're only going to get one product from the next propagation step. Of course, if they weren't the same, you would have to consider the products from either resonance structure. Sometimes people call this radical allylic bromination because you put the bromine on at the allyl carbon. All right, so that's just another example of the same reaction, only we're selectively modifying the allyl position because that's where you get the most stable radical. Now this has consequences for the food industry, as we talked about last time. If you have unsaturated fatty acids that have double bonds in the backbone, such as this last portion of, I think we said it was linolenic acid, you've got hydrogens that are allyl to two different double bonds. And you're not necessarily, your oils aren't swimming in bromine with UV lights going on, right? That's not necessarily a problem. But we live in an atmosphere that's 25% oxygen. And oxygen you may have drawn in past classes with this nice, lovely Lewis structure that suggests that there's no unpaired electrons in oxygen. But actually, if you do the MO picture, you get to a point where you've got 2 electrons left, and I'm not doing the whole MOs for oxygen, but you get to a point where there's 2 electrons left, and there's 2 orbitals that are equal in energy. And so you have one option. You have these degenerate highest singly occupied orbitals, highest singly occupied molecular orbitals, and you got 2 of them. You can have the spins aligned parallel to each other. That's called a triplet state. You don't need to know that, but it is more stable. And then you can have a case where the 2 highest energy electrons have opposite spin, and they call that the singlet state, and that's highly reactive. So you will sometimes hear people talk about singlet oxygen. And singlet oxygen you can think of as a very reactive diradical. This doesn't quite capture it. It's hard to capture with a Lewis structure. To show you what I mean, maybe we'll go to the Spartan program and we'll just draw oxygen. Oh, you got to be kidding me. The molecule oxygen is not in the database. Well, that's silly. We can go look it up. I won't attempt to Google it, but if you want to see the MO picture for oxygen, you do have these 2 equal in energy orbitals. You run out of electrons, and the what is it? Is it Hund's rule that says that you fill up the orbitals one electron at a time until you run out, and spins should be parallel because that's more stable. So when spins are not parallel with these unpaired electrons, it's more reactive. So you can think of singlet oxygen as a diradical. So actually, it's quite easy for oxygen to abstract a hydrogen atom, and it will do so from the allylic position in these fats and oils, because the resulting radical is resonance stabilized. And then that radical can interact with, say, another molecule of singlet oxygen, or perhaps with the molecule that just abstracted the hydrogen to create a new bond. And now you've replaced a carbon-hydrogen bond with a carbon-oxygen bond. This is called organic hydroperoxide, and it can degrade into just having the OH there instead of the OOH. You don't need to know how that chemistry happens. But this tastes bad. So that's where rancid oil comes from, and it's a radical reaction. But again, it's just allylic, abstraction of an allylic hydrogen, because the resulting radical is resonance stabilized. And that's why the Skippy folks wanted to hydrogenate their oil, is because this won't go rancid. You can leave it on the shelf for maybe a year and take a spoonful, and it still tastes like peanut butter. Go ahead.
Could you go over the hydroxide, the hydrogen peroxide, as the OH step again?
So, sorry, here we're going to abstract a hydrogen atom with oxygen, the diradical. That will leave an unpaired electron behind, and it turns out we just made this. Then the unpaired electron from the other oxygen will create a new bond with the allylic carbon using the other unpaired electron. That creates the hydrogen peroxide intermediate. I didn't show you where the peroxide comes from, but it's a couple other radical reactions that we don't really need to worry about. Okay, so that's one example of radicals that you experience in your day-to-day life. And actually, there are some foods in which they will put preservatives that are designed to intercept singlet oxygen so it doesn't react with the food. I'm trying to see if we could go up and look at the nutritional label for Crisco. Crisco has some oil in it that is not hydrogenated, so they've added TBHQ and citric acid as antioxidants, and that's about preventing singlet oxygen from reacting with the double bonds that are in the oil, so that your Crisco doesn't go rancid. And it does, actually. I've seen Crisco that was on the shelf too long, and it's yuck. All right. Sorry, anything else we missed on modifying allylic positions? Yeah.
This might be a little off topic, but how does it stop? How does it prevent a radical?
How would it prevent a radical from happening? There are molecules that are fairly stable as radicals, so I guess we would need to I'm going to look up actually what TBHQ is. And then I'll draw the structure for it. But these, well, I'm not sure what it's not wanting to show me. Tertiary butyl hydroquinone. Sorry, checking Wikipedia. Ring that when you ask your professor a question, they just check Wikipedia. You're like, what on earth are we paying for? Yeah, so a lot of preservatives are called polyphenols. A lot of antioxidants are polyphenols, and the reason for that is if you abstract a hydrogen atom, the resulting phenol radical, phenoxy radical, is resonance stabilized. And actually, it could even lose another hydrogen as well. So this is why you'll often hear, if you pay attention, people talk about polyphenols as being antioxidants. In fact, the molecule that's supposedly associated is itself a polyphenol, so another preservative, resveratrol. Veratrol. You'll hear about it occasionally. It's found in grapes, and it is also a polyphenol, and you can form lots of radicals on those oxygens, and they're resonance stabilized, and they don't go on to react. So these are things that we might call radical traps. You trap the radical with something that's fairly stable, and the reaction's done. Good question. Others? Okay, the other major area where radicals matter in your life is the formation of polymers. So let's talk about polyvinyl chloride, or PVC. You may be most familiar with PVC in the form of pipes that people use for plumbing or for sprinklers. PVC is a fairly rigid polymer. It's also was formerly used for records. So if you hear people talk about vinyl, hipsters like to play their music on vinyl because it sounds better. It's polyvinyl chloride is the polymer that they're using. What is the structure of polyvinyl chloride? Well, vinyl chloride is just the olefin directly attached to chlorine. Polyvinyl chloride is a polymer where we have lots of subunits of vinyl chloride attached to each other, and the subunits I'm drawing in black, and the bonds between subunits I'm drawing in red. So each of these is a vinyl chloride subunit. How do you get from the vinyl chloride starting material to the polymer? Radical polymerization is generally used. So to do this, you need a radical initiator, and we won't really talk about what that radical initiator is, but we'll just use an R with a dot on it. It turns out it doesn't much matter because by far most of the polymer molecule isn't the initiator, it's the vinyl chloride subunits. So in the case of, let's see, vinyl chloride, the initiator attacks the pi star and breaks the pi bond, and it forms a bond selectively with the less substituted carbon so that the more substituted carbon can have the radical. Oops. In this case, the radical ends up adjacent to a chlorine. Chlorine's got lone pairs on it, and so that intermediate is actually resonance stabilized. Yeah. And then in a second propagation step, this radical with on carbon will attack another subunit of vinyl chloride. Again, single electron attacks the pi star. We make a new bond, and the radical ends up, I did it again. I wanted the undo button. the radical ends up on the more substituted carbon where it's more stabilized by, in this case, resonance. And you do this again and again and again until you run out of vinyl chloride, or until the elongating chain of the polymer encounters another radical and does a termination step. And so you can control the length of the polyvinyl chloride polymer, and that to some extent can determine its properties. As polymers go, PVC is fairly rigid. And it can break easily. This time of year is especially problematic. Well, earlier in the year is problematic. So when we first moved into our house in 2011, I put some sprinklers in. The sprinklers in the front yard were already there. The developers had done that and put a lawn in the front, but the backyard hadn't been done yet. And so Amber was like 9 months pregnant with Adam at this point. We were just moving in, and my father-in-law said, I know how to do sprinklers. We should do sprinklers. And so I decided that we should do sprinklers. It was a terrible decision. That was a terrible time to be doing sprinklers. It was really dumb and a really sort of dark period of my life. But in any case, you know that at the end of the year, before you tell the sprinklers good night and turn them off, it's a good idea to blow the water out of the sprinkler lines, because water expands when it freezes. And if your sprinkler pipes are made of PVC, that expanding water can create cracks. So one year I said to myself, I didn't have an air compressor. I didn't want to go rent one from Home Depot or wherever. So I said, I'm pretty sure it'll be fine. This was a mortgage insurance or whatever commercial during the Super Bowl, or Tracy, whatever it is, was pretty sure that things were going to happen. Anyway, I was pretty sure it'll be fine. It'll be fine. Well, it was fine for the whole winter. But then when I go to turn on the sprinklers in the spring, I pressed go on the little box, and suddenly the sprinklers aren't happening, but suddenly water is gushing up from under the lawn onto the driveway. Like the lawn is literally lifting up underneath this torrent of water. And upon further investigation, I discovered that not only had the PVC pipe cracked, but it had totally shredded itself, like twisting cracks in multiple directions, because the PVC pipe was rigid. And so I learned that you have to blow out your sprinklers. You can still see in our lawn today, 8 years later, the spot that's a little lower because I had to dig out the sprinklers and then I ran out of dirt, and so the lawn is lower there than it should be. And it's a reminder every time I drive up to my house of the perils of not blowing out your sprinklers. This time of year, though, is when I have to start it up again, and I did blow out the sprinklers, but there's always some problem. I always end up taking 3 trips to the hardware store, and sometimes I end up needing to take a whole day off work just to get it done. And sometimes there are words that are not so good that are muttered. This time I'm trying to hold on to myself, and maybe I'll do it while conference is going this weekend, so that if things go bad, I'll still have some inspiration. Some hoses are made out of PVC and they tend to crack with time. This is because they put in the polymer a molecule that's called a plasticizer that gets in between individual polymer chains and sort of allows them to be less rigid. But the plasticizer leaches out. And so if you've had a hose that's been around for a few years, been in the sun, you might turn it on and the hose is now squirting all over the place in various, not on the end, and that's because the PVC is starting to get more rigid and crack. Anyway, we are done with Study Guide 12. We will finish up just a little bit more on 15 on Monday, and we'll move on beyond that.